It's a pleasure for me to talk today about MSC's solution for additive manufacturing and to introduce a brand new product called Simufact Additive. And of course, MSC has been involved with structural analysis for a very long time, providing solutions for you for modeling material behavior and also working with our partners Digimat, for manufacturing technology using tools from Simufact and tools from Marc, for structural analysis and multi-physics analysis using, of course, MSC Nastran and the Marc product, and for durability using the latest technology in MSC Nastran and MSC Fatigue. And really our objective is really to help you to go from material to manufacturing, whether or not it's induction heating or tube rolling or extrusion, to now also into the area of additive manufacturing, to simulating parts, including the effects of the manufacturing, to simulate full assemblies, welding of assemblies, joining of assemblies, and of course full system analysis, such as we do in automotive NVH or in atoms work or in aerospace work as well. So I think most of the people on the call probably are aware of additive manufacturing, but we'll just do a quick summary. What is it? It's really constructing parts and assemblies by adding material, usually in a layer-by-layer basis, and that differentiates it from conventional manufacturing, or sometimes called subtractive manufacturing, where we take a block of material, a cylinder of material, and we mill it and drill it and grind it, and we end up leaving material on the shop floor. So one of the beauties of additive manufacturing is what we say in the aerospace industry. It improves our buy-to-fly ratios. We leave less material on the shop floor. Additive manufacturing has been applied really first in the area of plastics, but today we're going to focus on metals. But later on in 2017, MSC will also provide a simulation tool for the modeling of plastics and composites using additive manufacturing. Additive manufacturing has also been used in ceramics, and it's even been used in the area of food products, but that is not the particular interest of MSC. So why additive manufacturing? A lot of this came out of the world of rapid prototyping. So additive manufacturing allowed us to make very efficiently small batches of parts. And the reason for that was additive manufacturing does not require tooling. So you don't need to build dies, you don't need to set up new hardware. So if you're only interested in a few pieces, additive manufacturing was very beneficial. Of course, one of the things we want to do is we want to move from rapid prototyping in few batches to more production orientation. Another advantage of additive manufacturing allows us to manufacture parts that we could design but previously could not build. So we could use topology optimization. We could come up with very creative designs, interesting geometry, but you actually couldn't manufacture the part, or to use casting, it would have been very difficult to manufacture the part. We can see that it reduces the amount of material being used, either because of this innovative design process or the fact that we are adding material as opposed to subtracting material, and we're saving material waste. These processes tend to use less energy because, again, it usually takes less energy to add material than to subtract material, especially when your material is of very high strength, such as titanium. The ability to produce these new designs allow us to do lightweighting, again, lower material usage, but more significantly what it means is likely to have better fuel economy. Very valuable, again, in the aerospace and the automotive needs. There's ability, and we'll see that in a couple of examples, to be able to manufacture full assemblies as opposed to manufacturing individual parts and having to braze them together or weld together. So that means less parts, lower part inventory, and also improvements in the manufacturing. There's this one about agility to manufacture parts anywhere. It has some particular applications, but really society isn't quite to that stage yet. But there are some nice abilities to repair parts, especially using deposition methods. And there's some nice ways of producing functionally graded materials, either through novel designs like this, where the holes are smaller here than the holes are there, or in deposition methods of actually using multiple materials. So we're going to see that additive manufacturing is going to allow us to go from larger design spaces to more novel designs that we can manufacture today. So we're going to take a look at, of course, some examples, some of which I think are very famous, and you probably know. The nozzle, which is really a functionally integrated piece that used to be manufactured in multiple parts, but now can be all constructed together. This little piece here, which is basically, it looks like a hose. It's actually used for biomedical applications. It used to be basically 13 links that were each manufactured and then hand assembled. Now you can do that all in one operation. Problems of turbine blades, nice to be able to achieve because we can put these cooling passages right into the blades. That's use of cooling passages also makes this very appropriate for constructing dies. And one can see that you can really form very intricate geometries, which before you would have done through basically bending different pipe sections and then, of course, weld them or braze them together. Lots of innovative designs are coming in through additive manufacturing. So we're going to focus on a few machines and a few pieces of technology. And the first one I'm going to talk about, which is really the goal of the Simufact Additive new product, is laser powder bed fusion. In such a machine, what we really have is we have a heating source. It's a laser, some focusing devices. And what we're going to do is we're going to initially have the powder on a platform. We're going to selectively heat the powder. The powder is either going to sinter or hopefully it's going to fully melt. And where we don't aim the laser, the powder will remain as powder, and otherwise it will be a solidified layer. The bed will be moved downwards, the platform. A new layer of powder will be applied, and we'll follow the process over again. So it's this process of continuously building up the material layer by layer that we're talking about in this type of additive manufacturing procedure. So in these machines, effectively, we have a finite size we can build, a size capacity. Newest machines go to as much as 500 millimeters. The material is in a controlled environment. And particularly, there's some gas, usually argon, to prevent oxidation of the metal. And when we do this process, you can imagine that effectively we're heating up the material. The material then cools down as the laser moves aside, or during the stage while we're putting on the next layer of material. Then we heat again. Perhaps the material at one layer or two layers down reheats. And so we continuously have this thermal cycling process. And due to that thermal cycling process, two things can happen. One is we can generate residual stresses in the part. And the second thing is our net shape that we desired is not what we actually obtain, that there are critical deformations in what we want to manufacture so that we may not be satisfied with our effective requirements. And there are a variety of hardware companies that are in this business, and of course if you're reading the recent news, there's obviously some consolidation and acquisition going on in the hardware world. The other machine that's quite similar, other technology, is the E-beam technology, and this technology can also be addressed by Simufact Additive. Can also be addressed by the Marc product as well. And the E-beam technology, of course, there are two big differences. One is it's a higher energy source. It's an electron beam. Second thing is the build capacity of the machine is smaller today. Because of this ability to achieve higher temperatures, we generally use higher strength materials such as titanium. The chamber itself is usually evacuated, though perhaps some argon is put in as well to prevent oxidation. We generally have a thicker powder and a thicker powder layer, so we tend to have some rougher surfaces, and we might need additional follow-on surface finishing to be done. The other technology has to do with deposition methods. In deposition methods, you can think of one deposition method that's been around almost for an extremely long time, which is welding. But these are all techniques that basically add material through either a wire or a rod or a powder and heat it with either a laser or electron beam or a gas arc welder. And the function of these, or the interesting things of these machines, is that they usually aren't in a shielded environment. We can generally form much bigger parts using deposition type methods. The key statement here is it's like welding technology. Generally, metals that are easily weldable are appropriate for this type of technology, and we'll just spend one more slide talking about these as well. So this technology here we can do with Simufact Additive and the Marc product. This technology here we use Simufact Welding product or also the Marc product from MSC Corporation. So these deposition machines have really been around for a longer period of time. In fact, the fused deposition type machine is known for as much for plastics as it is for metals, where we have a coil or a wire of material. It could be plastic, it could be a metal, and we basically heat it and deposit the material on. Other machines that are a lot in the news is the big area additive manufacturing. It's also fused deposition, but a larger bed. There are direct metal deposition techniques, and often they're combined with grinding machines or other types of machines to improve the surface finish. And there's this other EBAM machine, which is also quite well known for manufacturing larger parts. These are all processes that are better suited for either utilizing Simufact Welding or the Marc. So, manufacturing challenges. There are plenty of challenges associated with these parts. One, as I mentioned before, is the final net shape, the distortion. The fact that you thought you were going to have the correct shape and you didn't. Residual stresses, we're going to talk about those more in detail. The structural quality, especially in powder bed machines where we basically have this powder. The powder heats, it sinters, hopefully it actually melts. So that means that we get a more homogeneous material. If we have any sort of pores left in the material, those pores can be nucleation points for fracture and reduce the fatigue quality as well. A lot that we do here is we do additional heat treatment, and we'll see how Simufact Additive can help you with those problems as well. Another area is the high learning curve. We have more experience with methods such as milling and forging than we do in additive manufacturing. Some of these machines have a large number of parameters that we can choose from, up to 200. What is the orientation that we want the parts? What is the support structure? What is the power that we want to apply? What is the material, etc. are involved. The build speed, of course, influences things. If we have a certain power, we run the speed at a slow speed. Of course, that generates greater heat. If we are too slow, we actually might get some vaporization, which is not good. So we want a reasonable speed. We want reasonable production rates. Quality control, big issue. Powder size, control of the thermal device. Simufact Additive and our simulation products can't really control the size of the powder. Higher material costs, the fact that we're using specialized materials. The good news is the material costs are reducing. Size limitations I talked about earlier. Surface roughness, which might require secondary finishing operations. And we're often interested in the microstructure evolution so we can determine what the material hardness is going to be. So a couple of examples of this. This is where you work with an organization called Endes. Endes is a reseller of EOS machines. It's one of the partners that we are working with. And of course, the first one is really distortion, the fact that we wanted this to be nice straight sections. We'll see later that we are able to predict that amount of distortion. It's out of tolerance. We can't assemble the structure correctly. Or we have large residual stresses in the part. Those residual stresses might be at the base where we're connected with the support structures, or it might be just anywhere causing this type of cracking structure, or the material might rise a little bit and it becomes, you get height distortion, and then you try to layer the next layer of material and you're not able to do that. And all these things lead to iterative process, iterative trial and error. And if we have to do that iterative process, we're going to lose time and we're going to lose money in the whole process. So what we are offering is simulation as a method to reduce this trial and error process. That we can use simulation so that we can get to better designs that you put into the machine such that your net shape is the desired shape, that you don't have the residual stresses that might cause cracking in the structure, that you can investigate the residual stresses not only of the building up of these powder layers, but also the thermal process, the heat treatment process, the cooling process, the HIP process in the simulation. So it's not exactly easy. There's some people who suggest that it's impossible to do any simulation of additive manufacturing. There really are 4 issues, and I kind of want to quickly go through them. One is this is a thermally driven problem. It really has to do with your heat source and how you're basically influencing the material behavior, whether or not you're laser, electron beam, or gas metal arc welding. The second thing is the material itself. It's a complicated process. We have sintering of the powder. We have melting of the powder. If our temperatures are too high, we have vaporization. If we have vaporization, we generate smoke. That influences the thermal efficiency of our heating device. We have phase transformations occurring in the structure. And of course, we have this powder that's effectively compacting as it's doing its melting process. The other issue that makes this challenging from a simulation perspective is we have different orders of dimension scale. We can think about grain size, and that's important in terms of the final hardness of the product. We can talk about the powder, and the powder is a fraction of a millimeter in size, depending on which technology that you use. The fact that we layer up the powder in multiple layers, and again, the layer thickness is a fraction of a millimeter. We can look at the heating area and the heat affected zone or the melt pool, and that also is a critical dimension, one of the more critical dimensions. And then we can talk about our engineering part. And our engineering part, yeah, we'd like to build as large a parts as possible, especially for some industries. So we have this large ratio of scaling of sizes. If you think about this layer thickness, the number of layers easily be between 1,000 and 4,000 layers. The second issue is time scale. We have multiple time scales. So people who are used to simulation, used to finite elements or any technique, well, if I talk about speeds of the heating device, laser beam, 7 meters per second, E-beam, much faster. The time to traverse this melt pool or the heat affected zone is very small. The time to do a layer, depending on the machine, the technology, 5 to 10 seconds. The time to manufacture our engineering part, 2 to 24 hours. So if you would think about doing a traditional numerical simulation, again, you would say, I need to do a lot of increments. I need to use a lot of computational time. Is this achievable for what I need to do to improve my additive manufacturing method? So we're looking at providing you multiple solutions to solve this particular problem. And the analysis approaches that we talk about is the micro scale, looking at each particle, tracking each one of the hatch lines, whether or not you're doing unidirectional hatches or bidirectional hatches or these checkerboard hatches or at different angles. That's extremely expensive. If you wanted to manufacture a full part, very difficult to do at the micro scale level. We talk about mesoscale level, where we group multiple hatch lines together. We group multiple layers together. We have an effective thermal heat transfer model. That's what we've conventionally done in processes like welding processes. We're going to show some examples of that just to demonstrate that we can capture very accurate results. And in Simufact Additive, which we're introducing today, we're going to talk about using almost conventional structural element size. So you can tune the element size, but we're going to get computational times that are very quick, especially very quick in comparison with micro-scale analysis. So the big thing about our macro model, we're going to use bulk material properties, and we're going to use a method called inherent strain that I'll talk to about very shortly. And then, of course, full-scale analysis, where we really want to do the micro-scale. We really want to capture the low-level physics and, at the same time, build big models. So just on the thermal aspect, it's important to recognize when we talk about these powder bed processes, very complex. We have energy source coming in, we have all these little powders, we have radiation going through all this area. MSC has tools to solve that problem. The tool is called MSC Cinda, but we're not going to look at that. Even in the Meso analysis, we're going to use tools similar to what we've been using for many, many years for welding analysis through one of these well-known methods of particularly the Goldach's double ellipsoid method for heat transfer, or a deep cylinder, which is more appropriate for lasers, or combinations of these types of geometry to come up with effective heating in the solution. And what I want to really convey to you is these are very well-established technologies. So while this is not an additive manufacturing problem, it is very similar to it. We're building up this weld region, and in fact, there are 23 layers of material that's being built up, and in fact, each one of those layers is about 1 millimeter in size. But very detailed simulations and using thermal couples to predict, to do the prediction and do the measurement, basically show that we get very good correlation with the Marc program, and the Marc program is the technology behind Simufact Additive to predict the temperatures in these processes after 14 passes, after 18 passes. And not only that, while it's much more difficult to do the experimental process of looking at the residual stresses, the red and the blue curve, the blue curve is the finite element curve, the red is the experimental curve. These are then normalized data, but we get also extremely good correlation, even in predicting what the residual stresses are in parts that have had this type of thermal cycle behavior. And people have been using this technology for a long period of time with our products to do things like fused metal deposition, where we're effectively adding material, we add more material to the system, we basically do these types of simulations and have devices or mechanisms to evaluate what the temperature is, and again, we get very good correlation as we do pass after pass after pass, looking at the thermal cycles in this type of process. And people have also done extremely detailed simulations, really at the micro level. So this is really a 1 millimeter block, and there are like 50 elements in here, so we have elements almost down to the size of individual powders, but we're still using a continuum mechanics approach. And the things I really want to point out is really we can capture the thermal behavior. We get a non-symmetric behavior because some material is solidified, on the other side it's not. And we can predict the stresses and the residual stresses, and you'll notice the high stresses are really where we have the constraints in the system. And so we can really accurately predict this, and we can use that to give ourselves confidence on what we're doing when we're doing these other approaches. And really from that same type of study, we can actually follow the heat source, look at basically our hatch spacing, and predict the melt pool in the structure, and have very good correlation with the physical process. So we're going to use this technology with our new product called Simufact Additive. So who is Simufact? Simufact is an organization that MSC Corporation acquired in 2015. They've been a partner with MSC for over 25 years. The first product had to do with forming type of simulation, forging, extrusion, rolling, thick sheet forming. Then they introduced a product associated with welding, and now we're introducing a product called Simufact Additive. And what Simufact Additive does is it really does the whole process chain. Not only the buildup of the material in a powder bed fusion process, but also the heat treatment. And the heat treatment is very important if we want to improve our fatigue characteristics of the metal and to improve the fracture toughness of the metal. We can basically cut off the base plate, we can remove the support structures, we can model a subsequent step where we do a hot isostatic pressing. If we so desire, we can move the results into Simufact forming to do additional machining or heat treatment, or you can take the simulation and take that deformed configuration and move it into MSC Nastran, or you can take that deformed configuration with the residual stresses and move that into the Marc product. We can also take the results that we get through this process chaining and take those displacements, those deformations that were undesired, and feed it back to the design so that you give the manufacturing machine a compensated design so that when it goes through the manufacturing process, the final shape, the final net shape is your desired shape. And of course, with MSC Nastran, with SOL 200, we can do topology optimization to help you improve your initial design as well. So Simufact Additive is a very process-oriented program. It has a very easy graphical user interface. We will see a demonstration a little bit later. Easy to use, very quickly to be productive. You will see very fast modeling. We can do simulations from, depending on how the resolution of your model, from just a few minutes to a couple of hours. It will either import the support generation either from Magic or from NetFab or from Quantum AM, or you can build your own. It will automatically match the structure and, of course, provide a solution. So people ask, what is this inherent strain method? And the inherent strain method is not a new concept. It was actually introduced in the 1970s for welding of ship hulls. What it's based upon is this concept that we heat up a structure, we cool the structure, we introduce strains in that process, which result in the residual stresses in the process. And what we want to do is basically determine, based upon your process, what those inherent strains are, and then apply them in the analysis. So as I mentioned, it was really introduced as long as 1970. It was really used for a similar process for the welding of ship hulls, where the structure is very big, so we can't really do a micro-analysis if we have to basically model a 5-meter long section of a ship. Other people called it different names. Some programs you're going to hear the name eigenstrain method. It's the same as inherent strain method. It was first applied to additive manufacturing by these two gentlemen at University of Bremen. They actually used this technique, and they utilized Marc to get their first simulation. So what we want to do is we want to work with you to calibrate your machine and calibrate our software. So you basically manufacture 2 or 3 of these little cantilever specimens using your piece of hardware, your power that you're going to set the machine at, your speed that you're going to do your hatch pattern that you're going to use, and then you're going to build one of these specimens. You're going to cut it off or cut it in between and measure the deformation that occurs after you cut it off the base plate. And we're going to take that information and we're going to perform a little design of experiment simulation with finite elements. And we're going to back calculate what the inherent strain is for your process, for your machine, your powder, your parameters. And we can do that relatively quickly. Now what we're going to say is when you build other parts in the same hardware configuration, those inherent strains can work again. And if you want to use a different powder or a different power, what you'll need to do is recalibrate it, recalculate those inherent strains, and then Simufact Additive will form a database of all your different inherent strain values. So when you do that, you could then take a part, such as this aerospace bracket, and you could say, I'm going to have these parameters, therefore it's this set of inherent strain, and I get this simulation. And I'm going to set my parameters different, I'm going to use a different inherent strain, and I'm going to get this configuration. And in fact, this configuration results in lower deformation. You can also use Simufact Additive to look at what's the geometric configuration that I should put in the part. So I start with this STL, and you can see I built some support structures over here, and I do the simulation either in a vertical configuration or a horizontal configuration, and what we'll do is we'll predict that this one, at this point, with still the support structure included, has higher deformation in the analysis. And we can go through that whole process of orienting the part on the base plate, or the part design on the base plate, doing the additive manufacturing, look at the distortion after we've cut off the base plate, look at the distortion after we remove the supports, and decide what's the better configuration. Of course, some of you will say, yes, but I get a orthotropic configuration, and this might in fact be the configuration that I want the material properties. I'll say, that's okay. I can take this higher amount of distortion and I can help you predict what your compensated design should have been. Other things that we can do is we can take a look at that part and we can look at cutting it off the base plate, and we can see whether or not when we cut the part off looking in the X direction or cut it off in the Y direction, which one is more optimal in terms of reducing the amount of distortions in the configuration. And here, for this particular layup, it turned out that cutting it in the Y direction had resulted in less distortion in the part, and we can predict that with Simufact Additive. As I mentioned, we really are looking at the full process chain. So not only removing the base plate, performing some heat treatment, looking at the cooling of the process, removal of the support, doing a final HIP operation. We can automatically chain this, no restarting, no going to different simulation tools to look at the complete deformation and the residual stresses. We can also look at influence of support structures. So in this configuration, we had less support structures, we had more deformation. Here we had more support structures, less deformation. But it will allow you to do the trade-offs of saying, okay, I have more support structures, but now I have more work in removing the support structures after I manufactured the part. Or also considering not only the support structures, as a mechanism to make sure that we don't have any collapse, but recognize that when we do the heat treatment, that the support structures are used to convect heat out of the system. So additive manufacturing simulations, what it allows you to do is really explore those possibilities. But what it can absolutely do for you is basically say, clearly didn't have enough supports, my circular tube turned into an ovalized tube. Clearly in this particular part here, where I wanted a straight segment, clearly it's predicting more distortion in this area, which exactly matches where the distortion is. In problems, what we're able to do is, you hardly can see this, but you would see a line in the simulation which closely aligned with effectively a crack in the part. But other types of cracks in high stresses, we can correlate with cracks that occur in the material or at the attachment points in the material. Once we do the simulation, that's not the final objective. The final objective is to help you come up with a design so that when you do the process, you have a good part. So here we did the process, we did the simulation, we noticed, very hard to see, that we get a little bit of distortion. We take that amount of distortion and we effectively subtract it from your original proposed design. We do the simulation again, and you can see now the distortion is substantially reduced, so our net shape is truly our design. So Simufact Additive really can go through this whole process of manufacturing, doing heat treatment, cooling the part, and removing the supports. See here, as you see this voxel mesh, so we have an automatic procedure to generate the voxel mesh. We have a procedure to generate the support structure. We have techniques so that the voxel mesh can accurately predict the structure of the material, and then we project the results onto the final deformed configuration. We can do this for very complex parts, such as this manifold. This was an example working with our partners Rennie Shaw. So in the older processes, you might have not even be able to build this part so easily. You might have built it by taking a collection of tubes and sheets and joining them together. And you can see in additive manufacturing, what we can do is we can form that whole part, that whole assembly at once. Talked about topology optimization. It's very critical in this whole value of additive manufacturing because we can design new parts. So if we would have had a design space like this, we could have used MSC Nastran to tell us where we can remove material. We get information like this, tells us that the material is to be removed. We have tools to basically smooth your geometry. We can then take that and generate finite element meshes for CAE analysis, or we can take effective smooth geometry and we can say, let's do additive manufacturing prediction. So here, this is using a finer mesh. Here the element size are 1 millimeter in size. And here is the manufacturing process. We're basically looking at our desired shape. We're filling up the shape one layer at a time. And then we cut off the base plate, and then we remove the supports, and we would have been able to determine what are the distortions relative to the desired shape.
In the next few minutes, I will show you how to set up a 3D printing model with Simufact Additive. The first, what we have to do is to select a machine to know the build-up space and to link it to the parameters. we will use a macro scale simulation. And finally, we have to define here the stages which we want to use in our process chain. We will do 2 support removable steps. Then we can import our part. We have different interfaces available from STL over IGES and STEP to direct interfaces. Everything is unit-based, so we can select the unit in which the data are stored. To read it in, the part is then automatically positioned in the build-up space. The next is to define the support structures. We can do this automatically within the program or reading in cut information or STL files also from Magix and NetFab. When this is done, we can assign the material, which we will get from an independent material database. The next step will be the definition of the manufacturing parameter. For the macro scale simulation, we have to select the inherent strain, define the layer thickness, starting angle, and the incremental angle for each powder layer. When this is done, we can define the cutting direction and the height where we want to cut the part because it has an impact to the final distortion. The next step is that we have to select the support structures we want to remove in the first step and the last stage. When everything is done, we can create our voxel mesh. The voxel mesh is scalable. As bigger the size is, as faster is the simulation. So you can do a pre-optimization and later you choose a smaller voxel size. When everything is defined, the arrow gets green and we can start with the simulation. Everything is done for the model set. We start the simulation, and when the first increment is available, it will automatically switch to the post-processing view. So now the simulation is running layer by layer. We are assigning the inherent strain and calculating the distortion and the residual stresses out of it. Within the main control bar, you can switch directly back to your CAD model. You can have a look to your mesh, or you can go to the post-processing. So you can switch very easily. We have multiple post variables available, which you can change here. We also have some AM specific post variables introduced in the software. If you want to scale it, you make a double click, and then you have the possibility to do everything which is common for the lead sheet. You can track post variables. They also will be switched when you change the variable. Now, when everything is done, for the 3D printing process, we will start with the cutting. At the end of each step, we will automatically track the results to the initial shape, also the distortion, so that we get at the end a smooth shape of the real printed part. In the cutting process, we start from the right side to the left side. The residual stresses will get free and we will see the distortion at the end. When the cutting is done, we will remove the base plate, and after we have removed the base plate, we are removing the support structures, starting with the upper support structures, and then we will remove the support structures which are inside the part. Now the whole simulation is done. It takes at the end 137 seconds wall time. We are running this in a parallel mode. We can export the file now by compensating the displacement and use this as a pre-distorted shape for another simulation. If you want to run a variation, you can easily copy the process and change parameters and run it again. Thank you for your attention.
Really, in conclusion, MSC is providing you with tools to simulate the additive manufacturing process. And these tools can be used to improve your productivity. Simufact Additive with a new product, it will be released this month, is easy to use, and it can be used to quickly predict distortions and residual stresses in your model. It can be used to help you compensate your design to get your final net shape process, and it will help you to reduce your trial and error process that is timely and spends money. So for more information, you can go to either the MSC website or the Simufact website, or contact Volker Mensing at Simufact or myself at MSCSoftware.com, or contact your local MSC office or our worldwide distributors. Thank you very much for your attention.
Thank you very much, Ted. At this time, please type in any